Let's do one more problem. In this case, we have this water which has been heated inside an insulated and also constant denominator, the diameter tube. We're given that this is a 5 kilowatt electro resistance heater. Hint right there. That is Q dot is equal to 5 kilowatts. Okay. Another thing is that it enters at 15 degrees Celsius and it leaves at 60 degrees Celsius. So we know that we're gonna have a change in temperature. Okay, this is my initial temperature, and this is my final temperature. So just like I've said before, final temperature minus initial temperature, which is equal to 60 degrees Celsius minus 15 degrees Celsius. And if we do the math, then that is equal to 45 degrees Celsius or 45 kelvins. They want us to find the mass flow rate, right? We know we have this formula: Q dot is equal to M dot Z delta T. But in this case, we have the rate of heat transfer, we have the change in temperature, we are looking for the mass flow rate, and we don't have the specific heat. Technically, we don't, right? But we do have a table to which we can go to and look for it. So for this problem, we're just gonna assume that hey, water is right here, and we're just gonna take the value of the value of 4.18. We're just gonna say this is at room temperature. So then, specific heat in this case is just going to be 4.18. Let's look at the units. 4.18, and specific heat is kilojoules. Okay, kilojoules divided by kilograms times kelvins. So kilojoules divided by kilograms times kelvins. So all we do is just plug in the information that we're given, and we should be able to find the solution. So we have Q dot equals to M dot C delta T. So what I'm going to do is that I'm going to divide both sides by specific heat and change in temperature. So what happens is that this cancels out with that, and I end up with just M dot on its own. So M dot is equal to Q dot over C delta T. So now I just gotta plug in my value. So M dot is equal to 5 kilojoules per second. Now remember that we've gone over this where we know that 1 watt is equal to a joule per second. Okay, it's changing the watts into joules per second. But since I have a kilowatt, that is going to be kilojoules per second. And then the specific heat is just 4.18 kilojoules divided by kilograms times Kelvin. And my change in temperature is 45 kelvins. Now units that cancel out are just kelvins. Kilojoules cancel over kilojoules, and I think I've gone over this before, but I guess it doesn't hurt to do it all over again. Let me just divide everything. So M dot is just equal to 5 kilojoules per second, and so if I was to multiply 4.18 times 45, what I would end up getting is 188.1 kilojoules per kilograms. Now m dot is just equal to, if I divide 5 divided by 188.1, I get 0.026, and I think 5.81605 kilojoules divided by seconds divided by kilojoules divided by kilograms. Now let me put a pause right here. Okay. I have a fraction being divided by another fraction. The way to work with this type of problems is that you have kilojoules divided by second, and we have a big division. So kilojoules divided by kilojoules divided by seconds divided. So I'm gonna replace that by just this division symbol. Kilojoules by kilograms. I know I can't divide fractions, so I have to change this division symbol to multiplication. And if I do that, I have to do the reciprocal of those fractions. So kilojoules per second times, okay, again, I change this into multiplication, and then I'm gonna flip this fraction. I'm gonna do the reciprocal. So kilograms divided by kilojoules. Now what happens is that the kilojoules cancel out, and I end up with kilograms per second. So then my entire answer is just mass flow rate is equal to 0, it's just equal to 0.027, let's just put it as that, kilograms per second, and that is the mass flow rate.